All right, here's an example of a diagram showing simple harmonic motion. This could be a spring bouncing up and down or a pendulum swinging back and forth. We see here in the middle of the graph, this is graphed vertically. In the middle of the graph, I have zero displacement. And then over to the right, I have a positive x displacement, and over to the left, I have negative x displacement. So this would be a good diagram for a pendulum. As it swings to the right, it displaces in the positive x direction, and then as it swings back to the left, it displaces in the negative x direction. These little red arrows here, these are the velocity vectors. As a pendulum swings, it has its greatest velocity in the center of the swing, and then as it swings closer to the maximum displacement to the right, it slows its velocity until the velocity at the end of the swing, or the furthest displacement, is zero, and that's where it is briefly a velocity of zero, and it turns around and starts coming back the other way. So we see our velocity vectors now point to the left because the pendulum is swinging to the left, and the velocity is increasing. The magnitude of the vectors is getting larger until at the center point again, the velocity is greatest, and then it slows down again as it gets to the farthest negative x displacement. The velocity is zero once more, and then it speeds up back toward the center and slows down as it reaches the positive x max displacement. If I choose to start at this point right here, I would have a maximum positive x max displacement, and it goes to zero and then to the negative x max and back to zero and to the positive x max and so on. It's swinging back and forth between positive x max and negative x max. So this is a graph of its displacement as a function of time. Okay? Let's go over some of the vocabulary associated with this. How many times does the pendulum swing per second? How many oscillations per second? We call that the frequency of the oscillation, and we give it a unit of hertz, abbreviated Hz. So 10 hertz would be something that vibrated or went back and forth 10 times every second. The period is the time it takes for one complete oscillation. And we see that the relationship between the period and the frequency is that they are reciprocals of one another. In other words, taking the example of a frequency of 10 hertz, if something vibrates or oscillates 10 times per second, then each vibration or each oscillation will be 1/10 of a second. There's 10 oscillations in a second, so each of them is 1/10 of a second. If there were 5 oscillations in 1 second, then each oscillation would take 1/5 of a second, and so on. So the relationship is the frequency and the period are reciprocals of one another. Let's look at some examples. Okay, so I clicked down in the lower left corner where it said animation here, and it took me to this website, this YouTube page. This is a little movie or a little animation showing a spring oscillating and the displacement, the velocity, and the acceleration as a function of time as it's happening. So you can see at the endpoints of the oscillation, let me start it over here. At the endpoints of the oscillation, I have maximum displacement at the top and at the bottom. This graph shows me how the velocity varies throughout the oscillation, and this graph shows how the acceleration varies throughout the oscillation. And I'm going to start it over again. Notice that the acceleration is maximum when the displacement is maximum, and the velocity is zero at the maximum displacement, and maximum velocity at the what's called the equilibrium point, or the midpoint of the oscillation. I've clicked now on the movie link in my PowerPoint slide, and it's taken me to this YouTube video called Spray Paint Oscillator, and it's going to show us an oscillating spring that has a paint can attached to it. So basically what they're going to do is let this can of spray paint oscillate up and down while they move the paper behind it past it. And you see the result is a sine wave. All right, here's the next slide in the presentation. These three diagrams show comparisons of two different oscillations. The first one, we have different amplitudes only. So you can see here how far the oscillation displaces from the zero or the equilibrium point is different. So we say that the amplitude of the oscillation is different for these two. The amplitude being the displacement from the equilibrium point or the center point. In figure B, we have different periods. Period, remember, is the time of the oscillation. So you can see here for the blue oscillation, the time it takes for one oscillation is twice that of the red curve. The red curve oscillates twice within the same time period, and the red oscillation only occurs once. So these two waves have different periods. And then in the third one, the phase is different. So you see the amplitudes of the wave is the same, the period is the same, the amount of time it takes for an oscillation to occur, but the phase is just where we decide to start looking at the oscillation. All right, here's the next slide of our presentation. This is relating the angular frequency, which we represent with the letter omega, to the oscillatory frequency, F. So the oscillatory frequency is what we were talking about earlier, that it's the number of oscillations in a unit of time. 10 hertz, for example, means it oscillates 10 times in 1 second. So here on my y-axis, I will have an oscillatory frequency of the going up and down, and on the y-axis of my cosine graph, I will have an oscillatory frequency going up and down. Let's run the animation so you can see it at work here. And you see here on the y-axis, on the purple screen, I have an up and down oscillatory motion. That would be up to down to up would be one cycle of oscillation. Same thing here on the green screen. From highest to lowest to highest would be one oscillation. And the number of times that would happen in a second would be my oscillatory frequency. But here you can see that this sine and cosine wave can be created by a rotating wheel. So you know that there are 2 pi radians in one rotation of a circle. One time around a circle is 2 pi radians. So if I go through one complete cycle of the sine wave, I also go through one complete rotation of the circle, which is 2 pi radians. So we can describe the position on the sine wave by the position of the circle in radians. So radians in a full circle divided by the period is the radians per unit of time. So I'll just use the time and the radians for one complete cycle. So in one complete cycle, I have 2 pi radians, and the time it takes for one cycle, by definition, is the period. So radians per unit of time is 2 pi radians per period. And since 1 over the period is the frequency, remember that frequency and period are related in that they are reciprocals of one another. I can replace 1 over t with f, and I see that my angular frequency of an oscillation is equal to 2 pi times the frequency. All right, on our next slide, we look at the equation that describes the sine graphs or the cosine graphs that we're looking at. Realize that we call it cosine because this is the way we've chosen to start the graph at maximum displacement, just like the cosine graph does. But really, a cosine graph is sinusoidal in nature. So you might hear me say sine curves or cosine curves. Just know that it's all sinusoidal, and we're talking about simple harmonic motion. Okay, so here's the equation for this graph. It has amplitude, it has angular frequency, and it has phase. So for a given wave or a given oscillation, those will be constants, and what's varying is time. This equation is the general form of a sinusoidal waveform. So specifically for displacement, the amplitude is x max, the maximum displacement in the x direction. So its position x, or displacement x, as a function of time is equal to the maximum displacement times the cosine of omega t plus phi. We know that velocity is the derivative of displacement with respect to time. So down here we've taken the derivative of this equation 15.3, and we know that the derivative of cosine is negative sine, and then we multiply it by the derivative with respect to time of what's inside the parentheses. So that would be omega. So our velocity equation then is negative omega x max times sine omega t plus phi. And to come up with the equation for acceleration, we take the derivative again with respect to time, and the derivative of sine is cosine, and multiply times the derivative of what's inside the parentheses changes this omega to omega squared. And we get our equation for acceleration as a function of time, negative omega squared x max cosine omega t plus phi. Later in the presentation, we'll show you an Excel spreadsheet that mathematically calculates these equations, stepping in increments of 0.001 seconds, and graphs them for us so that we can plug in numbers for x max, omega, and phi, and see what the corresponding displacement, velocity, and acceleration graphs look like. I've set up a Excel file that graphs the equation x max times the cosine of omega t plus phi for displacement, and for velocity, my equation negative omega times x max times the sine of omega t plus phi, and down here the acceleration negative omega squared x max times the cosine of omega t plus phi. So you can see all the graphs, and here you can enter the amplitude, the frequency, and the phase shift as a multiple of pi. So if I wanted a phase shift of pi, I would enter 1 here. So let's go ahead and just see how it changes if I change my amplitude to, say, 1.5. Okay, so you can see the amplitude of the wave changed to 1.5. I still have only 1 cycle per second, so my frequency is still 1. If I change that to 2, then you can see now in 1 second I have 2 cycles, or 2 oscillations per second. And of course, if I change that to some other number, let's try 4, there you go, you see I get 4 oscillations in 1 second time interval. Okay, so I'm going to put this back to 1. And here, I let Excel calculate omega for me. Remember, omega is 2 pi times the frequency.
Let's talk about this variable here, the phase constant or the phase angle. Basically, all this is the starting point where time equals 0 is on our graph. So let's use Desmos to help explain this. So I'm using 2 pi f for omega. So my amplitude of my wave is 1. You can see that. 1 is my amplitude. Then 2 pi times the frequency is my omega value. So my frequency is 1, which shows 1 cycle in 1 second. And then my phase angle is 0 here for the first equation. So when time equals 0, the cosine of 0 is 1, and that's what I've got. But if I change my phase angle to be pi over 2, now when time equals 0, I have the cosine of pi over 2, which is 90 degrees, which is 0. So let's take a look at what that would look like. And there we have, at time equals 0, the value is 0. In other words, I have shifted the starting point at time t equals 0, which was at my maximum. Now it is at 0. So I shifted it from here to there. I shifted it forward in the positive direction by 90 degrees, or pi over 2 radians. So in effect, that makes the graph look like it went left because the starting point went to the right, and so I had to move the graph to the left to put that starting point on the t equals 0. Now if I use pi, let's try and predict where will the starting point be with a phase angle of pi. If this is where it is for 0, I go ahead on the graph, pi radians, so that would be right there. So let's take a look at that one. And we see that that is now the starting point at time equals 0. And pi over 3 is 60 degrees. The cosine of 60 degrees is 1/2. So that's what we see now at when time is 0. It's the cosine of 60, which is 1/2. Right there is my starting point.
Okay, so now what we're going to do is we're going to take our equation for displacement and we're going to take our equation for acceleration, and we see that in my equation for acceleration I have x max cosine omega t plus phi. Well, that's exactly up here what the displacement as a function of time is equal to. So I'm going to take this whole part of the equation for acceleration, and I'm going to replace x max cosine omega t with phi plus phi with xt. And so that's what I get when I do that. That says the acceleration at some point in time of my oscillation is proportional to the displacement. Okay? So whatever the displacement is, I multiply it by negative omega squared, and that is the acceleration at that same moment in time. This is the hallmark of simple harmonic motion. It's an extremely important equation, and it shows us that the acceleration and the displacement are proportional. Notice also this negative sign tells me that the acceleration has a sign that is opposite to the displacement. So if my spring is displaced in the positive direction, the direction of the acceleration will be in the negative direction, and vice versa. If I'm displaced in the negative direction, the acceleration will be in the positive direction. You know that acceleration and the force that causes acceleration are always in the same direction. So that means the force is always in the opposite direction as the displacement. This is known as the restoring force. And whenever a spring or a pendulum is displaced from the equilibrium point, the force is always trying to push it back towards the equilibrium point. We call that the restoring force. And that shows up in the equation by the fact that the acceleration has the opposite sign of the displacement. All right, our next slide deals with section 15.3 from the book, the force law for simple harmonic motion. So we'll start off using the example of a mass oscillating on a spring. We know that the force is equal to mass times acceleration. That's Newton's second law. We'll take our equation for acceleration that we had from the previous slide that said acceleration as a function of time is equal to its displacement times omega squared times negative 1. And we'll replace A with what it's equal to, negative x omega squared. And I'll just regroup the variables, and so that I have F is equal to negative m omega squared times x. Well, if we relate this to Hooke's law, we know that F force is equal to negative kx. So we look at these two equations, and we see that m omega squared is k. All right? So knowing that k, the spring constant for the spring, is equal to the mass that's oscillating times omega squared, I can solve that for omega, and I get omega is equal to square root of k over m. And we know that omega is equal to 2 pi over the period, or 2 pi times the frequency. And so I can solve this equation now for the period. That tells me that the period is equal to 2 pi times the square root of the oscillating mass over the k constant. Or if I know the spring constant and measure the period, I can calculate what the mass of the object is that is oscillating on the spring. Here's an application of this aboard the International Space Station.
Hello, Jeff Williams on board the International Space Station. We often get the question, how do we weigh ourselves in space? If you know the properties of a spring, then you can measure the mass. And it's a very simple problem of physics, and that's what we use here. We have this machine here that's got a known spring constant, and we've got it set up here, and I'm going to release it. And you're going to see it's going to oscillate at some frequency here, and we're going to go through a calibration. It's going to release. You see it's got a very predictable frequency here, and it's calibrated itself now. And we have an electronics unit over here that gives a readout of the weight, and right now, like I said, it's calibrated. So I'm going to reset it, and we're going to change it to working mode to measure the body mass. I'm going to get on it, and now since we've got my mass on it, the frequency is going to be much less than it was during the calibration, and it will take that frequency, the known spring constant, and calculate my mass. So here we go. And after about 4 calculations, we have a readout, 81 kilograms, a little more than that, 81.5 kilograms.